All right, so let's look at the applications of the Pythagorean Theorem. We've been doing a lot of stuff with Pythagorean Theorem. So what we're going to look at in this particular paper is applications of it. So how do we apply the Pythagorean Theorem to certain types of word problems? So what we're going to do here is start off by identifying the Pythagorean triples. Now the Pythagorean Theorem, if you remember, is a squared plus b squared equals c squared. Now that's the Pythagorean Theorem. Most of the time when you ask somebody what the Pythagorean Theorem is, that's what they're going to spit out. And we want to have a greater understanding of what the Pythagorean Theorem actually represents. What the Pythagorean Theorem is it's a representation and a comparison of areas. Whenever we say something squared, the reason that something to the second power is called squared is because what you're doing is you're finding the area of a square when you square it. A squared is the area of a square that is a by a in dimension. B squared is the area of a square that is b by b in dimension. C squared is the area of a square that's c by c. So 5 squared is the area of a 5 by 5 square, which is 25. 4 squared is the area of a 4 by 4 square, which is 16. So that's kind of getting the idea. So when we look at the Pythagorean Theorem itself and we look at the representation of it, I'm going to go ahead and show you right quick what we're looking at. So let's say Pythagoras and all these Greek mathematicians, they didn't have cell phones and tablets and iPads and whatever else it is that we have now. So they sat around and they just decided to test out these theories. So the Pythagorean Theorem is actually a comparison of areas. So basically what the Pythagorean Theorem says, if I have a right triangle, and I'll do my best on this, and I'm going to call this side A, that B, and that C. Okay, so what Pythagoras figured out is that if you compare the ratios of these squares, the areas of these squares, that you can form a right triangle based on the lengths of these squares, the sides, and that the areas are going to end up giving you the sums of 2 of the areas will be equal to the third. So for example, if I take a square that is an A by A, so that side is A, so we'll make this an A by A square. So the area of that square is A squared. Now we can look at this side. Let's draw a square off of here, and we'll make this a B by B. The area of that is B squared. And then we'll take the square off of the hypotenuse here, and we'll make that a C by C square, and the area of that is C squared. So what Pythagoras figured out is that the areas of these two squares, the two smaller ones, equals the area of the third. So that is where the Pythagorean Theorem comes from. It's not just some random a squared plus b squared equals c squared. It actually is premised on the sum of the areas of two smaller squares equaling the larger square. And when you have the area of two smaller squares added together and you compare it to the area of a bigger square, those 3 side lengths will form a right triangle. So anyway, let's look at the Pythagorean triples, shall we? So for the Pythagorean triples, 3, 4, 5. A Pythagorean triple is something we can look at. It's integers. It depends on who you want to debate with. We usually use integers. A Pythagorean triple is when you have a set of 3 integers that can form the side lengths of a right triangle. 3, 4, 5 is a common one. So if the legs are 3 and 4, the hypotenuse is 5. You won't have to apply the Pythagorean Theorem. Now by the same token, when we get into scale factors, if the scale factor is 2, that means if I multiply all the sides times 2, getting it to focus there, 6, 8, and 10 would also be a Pythagorean triple. Because 3, 4, and 5, if I double 3, double 4, double 5, I get 6, 8, 10. That will also be a Pythagorean triple. I'm using a scale factor and keeping it the same. I have to multiply all 3 lengths by the same number. I can't just multiply 2 of them by that factor and the third one by something different. So 6, 8, 10. So let's do a scale factor of 3 now. So I'd multiply 3 times 3, which is 9, 3 times 4, which is 12, and 3 times 5, which is 15. So those are my Pythagorean triples for 3, 4, 5. So that means if you can memorize these, you don't have to do the Pythagorean theorem. You'll actually know which ones create your triangles. You can actually just determine the lengths by looking at them. 5, 12, 13 is our next Pythagorean triple. So if I wanted to scale factor that by 2, that means that 10, 24, and 26 would also be Pythagorean triple. And if I do a scale factor of 3, that means that 15 and 3, so 36, 39 would also be a Pythagorean triple. So all of these are right triangles. We know they're going to be right triangles. Let's look at 7, 24, 25. That is another Pythagorean triple. If I double everything, that's 14, 48, and 50. If I triple everything, I have 21, 72, 75. All of these are right triangles. They're all Pythagorean triples. And they're all predicated on the basic Pythagorean triples, which is your first column here. So let's look at the last one. The last one, we have 8, 15, 17. So if I scale factor that by 2, that means 16, 30, and 34 is also a Pythagorean triple. If I use the scale factor of 3, that means 24, 45, and 51 are also Pythagorean triples. So that is your basic list of Pythagorean triples.